Let us start this session again. And this is the third and lecture by Professor Fritz Riehle. And he is continuing from the last two lectures.
Thank you very much. Yesterday, we talked about the introduction and basics of uncertainty in measurement. It was a more formal talk. I introduced also the guide to the expression of uncertainty in measurement, the GUM. And today we will put it, make a case study, evaluation of uncertainties in optical atomic clocks. Then I will try to talk a little bit about tips and to give tips and tricks to reduce errors and uncertainties in measurement. And finally, I would like to discuss uncertainties and errors in famous experiments. This is meant not only to point at particular experiments, because we all do mistakes, but rather to find out what can go wrong and to help us to avoid such pitfalls. Okay, in order to evaluate the uncertainty in an optical clock, we should first talk briefly about an optical clock. It is pretty much similar to the cesium atomic clock in principle, with the only exception that we do not have a microwave frequency generator, but rather a laser. We irradiate or interact with the laser is interacting with absorbers that can be atoms in a lattice. It can be free-falling atoms. It can be molecules. It can be single or multiple ions in an ion trap. And if we would irradiate such an ensemble, we would see some absorption feature in a detector. We could measure it, derive error signal from this, use a servo electronics to steer the laser to be at the frequency nu0. And then we have to, in an optical clock, we have to divide the frequency to bring it in the microwave region that we can use and derive the ticks of a clock. Okay, what is important? It is first the line quality factor that is given by the frequency nu0 divided by the line width of the transition. We asked ourselves about accuracy, and this means here how accurately agrees nu out of this here with the transition frequency nu0. We also can ask the question, what about the stability? To what extent fluctuates the frequency nu out around nu0? Let's talk a little bit about the noise and instability here. It is easy to imagine that the atomic transition has a very nice line shape, but typically you have a noisy line shape, and this you have to take into account. And a very simple approximation is what you do if you stabilize to such a transition. You first go to this side and to this side and to this side, and you compare the intensities. If the center, the frequency of your laser is maybe here, then it will be here if you go a line width across. So you are not at, you are not at the center, and you tune the frequency back towards the new node. And if you are have exactly the same intensity here and here, you believe you are exactly at new node. But this noise leads to noise in the frequency. And this we can calculate simply if we assume that we have a straight line here. So the sigma of nu is a signal to noise divided by the steepness or the slope of this transition. Typically, this depends on the form of the interrogation. It will be different if you would have a cosine function, for instance, for the Ramsey excitation, or if you would have a Voigt profile or anything else. So I use simply a factor of k in front of it that includes this, but it is typically of the order of 1. So factor of 2 or something like this. Okay, if we assume now that the signal to noise at 1 second is given by sigma I, and it depends, and it goes down if you measure for a longer time, like 1 over square root of tau, then you end up with a simple formula that gives you the signal to noise or the instability, gives you the instability at the time tau. Okay, let's make a few examples. So the signal to noise, if it is short noise limited, it depends on the number of interrogated particles. So if I would use 6 times 10 to the 5 atoms and the frequency of 9.2 gigahertz and the line width of 1 hertz, we have talked about this last night, then you would end up with an instability of 4 times 10 to minus 14 divided by a square root of tau. And you see immediately, if I would use optical frequencies, then this optical frequency is dramatically higher here. And if the line width is something like 3 hertz for a single ytterbium ion, we could come down to a much lower instability of 5 times 10 to minus 15, even for a single ion. But if we would use, let's say, 10 to the 4 neutral atoms, then with an optical frequency like this, and I will talk about these 2 standards in a minute, then we would come down to 5 times 10 to the minus 17 times divided by the square root of tau. And this is usually displayed in a so-called Allen variance. I will talk about this in a few seconds. You see, this instability limits your measurement accuracy. If you want to come down to, let's say, 10 to minus 16, then it would take you a month or so to do the measurement to put the instability of the cesium clock down so that you can compare 2 cesium clocks with 10 to minus 16. If you would use a single ion, and these are simply the factors I have calculated before, you can get this already in a few seconds. And if within an hour or so, you go down far below 10 to minus 17. And with 10 to the 6 strontium atoms or 10 to the 4 strontium atoms, you can get such comparison within a few seconds to very high accuracy. Okay, I talked about the Allen variance as a measure of instability, just to recall it. It makes you measure for a certain time, integrate the noisy signal for a certain time, then you do it for the next adjacent time interval. You take the difference of these two adjacent intervals, square it, take 1/2, and this is called the Allen variance. And of course, the Allen standard deviation is the square root of this. That's been invented by David Allen, that time at the National Institute of Standards and Technology in the US. How to determine the accuracy of a clock? So as I said, how accurately a grease knew out with nu naught. The frequency nu naught is the frequency of the unperturbed transition. So perturbations lead to frequency shifts, and frequency shifts lead to errors. And if we don't compensate for them, if we compensate for them, there is some residual uncertainty, and the total uncertainty you get if you look for all of the perturbations. And we will go through it in a minute. But because if you strive for the ultimate accuracy of a clock, you do not have a better clock to compare with. So what you have to do is to estimate the final uncertainty. And this means you have to think and sit down and think about all the possible contributions of an uncertainty budget. The uncertainty budget, of course, depends on your specific optical clock, and it also can change from day to day if one of the perturbations changes. So what do we need with optical clocks? Yes, we need, first of all, a super stable optical oscillator. Because if I want to interrogate an atomic transition within seconds, I have to make sure that the interrogating laser not fluctuates in frequency too much. Okay, but frequency stabilized lasers can, the best ones today can be below 10 millihertz or so. So in principle, it's not a problem, but it's hard to achieve it. And I work in this field still. It's my hobby. And if you are interested how we can do this, you can ask me afterwards. So the second thing I also talked about last night is the interaction time broadening. If I want to interrogate the atom for a certain time, this means that I have something like a truncated interaction. And this truncated interaction leads to a frequency width, and the frequency width I want to achieve should not be much larger than the width of the natural line width I want to measure. Okay, this means if we want to go down to a hertz or 10 millihertz or so, we have to store, we have to allow the interaction for at least 1 second or 100 seconds or so, which means that the absorbers I investigate have to be stored and by any means. The movement of the absorbers must not lead to frequency shifts by the Doppler effect. So usually you have to laser cool your absorbers. And the optical frequency has to be divided into the microwave domain, but optical divider today of femtosecond frequency comms is state of the art. Okay, let's have a look to the Doppler effect. Yes, sure. This is to the first order true, but to the second order, I remind you that in the cesium atomic clock, the line width is 10 to minus 10, roughly 1 hertz at 10 gigahertz. So the line width is one hertz, roughly. But they split the line to 1 million or so to determine. Yeah, so it depends how accurately you know your line shape. And if you if it is not asymmetric and all the things, you can find the center of the line shape much better than the resolution. But we are far from the 10 to minus 6 in the optical domain. I would be happy if I could say 10 to minus 2 or so. Okay, thank you for the question. The first order Doppler effect is a perturbation. So in a gas, you know, you have a Maxwellian distribution. And this leads to a broadening of the transition that can be dramatically high in the order of megahertz or even more, depending in the case of hydrogen, depending on the temperature and all the. To overcome this first order Doppler effect, you have to use Doppler-free methods and use laser-cooled absorbers. But there is a nasty beast called the second order Doppler effect. This is, if you look for simplicity, to a two-level atom where a photon is absorbed and puts the ground state atom with energy E1 and momentum P1 into the excited state. Then you can use energy conservation and momentum conservation to see that the frequency you need is not exactly this frequency, but also depending on the first order Doppler effect plus a recoil effect. And if we would use the relativistic energy and momentum conservation, and I do not bore you with the calculation, then you get another term depending on the velocity squared, which is called the second order Doppler effect. And this is a purely relativistic effect. You can also derive it from time dilation. So it's sometimes also called time dilation shift. And you can see this, what it does. It makes, first of all, a broadening, but also it is asymmetric. This is not a nice thing for a frequency standard, and it's clear, according to the discussion we had just a minute ago, that to find the maximum here or the transition, it's not easy. It's not allowed to take the maximum because this depends on the second order Doppler shift. You have to make, you have to allow for make corrections. Okay, how do we store the atom? This was a precondition to use optical frequencies. So you all are aware that there are optical lattice clocks, and this is simply to explain if you have a one-dimensional optical lattice, you can use a standing wave, and this has such a electric field distribution. You can do a two-dimensional optical lattice simply by using retroreflectors, and a three-dimensional lattice in the same way. An atom now, which comes near this field, if there is no electric field like here or small electric field, the atom will be like it is. But in the high field strength, it will be polarized. The positive charge and the negative charge will be separated of the atom. And it's obviously from the beginning that this leads to frequency shifts. So in this, let's consider now again the optical lattice, where the atoms then occupy minima in this lattice, or in this picture can also use maximum. Okay, in this lattice, we now, the atom, if it moves a little bit, it will see a parabolic potential. This means the motion of the atom will be quantized in the ground state and as well in the excited state. And so we have more than one possible transition. We can use a transition from the ground state to the ground state. That would be the center frequency. But we also could go from the ground state to the first excited state that has a higher frequency. You see this here, and or from the from an excited motional state in the ground state to the lowest ground motional state in the excited state, something here. And here you see already the influence of the second order Doppler effect. And the nice thing is that the center frequency, the line here, is free from the first and second order Doppler shift, because the motional state is, there is no motion in the ground state and in the excited state. Okay. Pardon me? It depends on the temperature. It depends on the probability with you can excite in the different states. For instance, if these states here are thermally populated in principle, if there is a high temperature, you can occupy a number of states. And if there is a very low temperature, you can only occupy the few lowest states. And what you can use, you can use this even to find the temperature, because yeah. Okay. So an optical strontium lattice clock. Let's briefly talk about this, because many experiments are done in India also with this. So you have a ground state, singlet as naught, and the first excited state in the singlet system would be singlet P1. The transition is 461, and you can operate a magneto-optical trap here nicely to make cold atoms in the ground state. The transition to the optical transition can be either the first transition you would use is 689 nanometer to the triplet P1 state, but this is the allowed one. But you know from basic atomic physics, it's not possible to excite the triplet P0 state because of the selection rules. Yes, if you add an H bar omega, the momentum, the spin of the photon has to be compensated, but 0 to 0 is not possible. Okay, why does the clock operate anyhow? So the reason for this is that there is a mixture to these states from the P states. So it's not a pure state. To some extent, there's a little bit. This is not only a pure triplet P0, but also an admixture of the singlet P1 state. So the transition is possible. There is also a hyperfine hyperfine interaction between these states, and this allows the transition. The transition then is a few millihertz, and this makes a very good quality factor to do this. So the second step is then you cool on the 689 nanometer line, and then you interrogate this transition. And then you have to set up the uncertainty budget of your strontium clock. And this is what I want to talk a little bit about. First, as I said before, the uncertainty budget of the strontium clock depends on your actual realization of the clock. This is the strontium clock that has been published in Metrology 2019 from the Riehle group. They end up with a fractional uncertainty, should mean fractional or relative uncertainty of 2 × 10⁻18. But also PDB operates a strontium clock, and I have looked at this a few years earlier, and then the budget looks completely different in a way that the total uncertainty is an order of magnitude higher. So it depends on the actual state how you operate your clock. And if you look for this, we have talked about factors already. So about the second order Doppler shift. Yes. No, the lattice, it's hard. Okay, that's the perfect question for a comment I wanted to make. If you operate it at the magic wavelengths, you can do this only with an uncertainty. You have to measure this transition, you have to measure this effect, and you have to make sure that your magic wavelength is exactly the same all the time. Yes, and so you have to estimate what the shift could be. And in this case, they came to the conclusion that this residual shift is of the order of 10⁻16, but they believe that they can correct it to an uncertainty of 2 times 10 to minus 19. Okay, as we discussed yesterday, you determine your correction, you subtract it because we don't make errors, I said yesterday, and then you have a residual uncertainty. But this is you, of course, because you calculated things like this, looked first of all to this. But okay, let's continue with this discussion. The magic wavelength is a fact. As I said before, if you put an atom in a strong magnetic field, electric or magnetic field, it will get polarized. This means that the energy levels in the ground state and in the excited state will depend on the laser wavelengths you use. But the fortunate thing that has been shown many years ago is that there is one frequency where both shifts are the same. They are really dramatic, minus 150 or 1 kilohertz, and we aim to go to Hertz also or below. And therefore, this wavelength is called the magic wavelength. It's okay. These are fermions. This also depends what kind of trap you use. If you have a trap that is tightly confined, you are perfectly right. Junier in Chile has shown that you have the Pauli exclusion principle then, but we often use standing wave only, one direction. And then in the other direction, you have the possibility that the atoms separate, and then you have can have a shift. But to come back to this, okay. So there is another shift called black body shift. What does this mean? If you calculate the electric field in this room at room temperature, it is like 800 plus volts per meter, really big, and the atoms feel this. Yes, and why do they feel this? Because the reason is the frequency is extremely high compared to the frequency of the thermal radiation. So there should not be much shift, not at all to the ground state, but there are other states here, triplet D, which are not very far away. And these can be coupled to the excited state in such a way that they shift the frequency of the excited state. Okay, what can you do with this? There are different approaches. You can measure at room temperature everywhere the temperature that has been done in NIST, and they claim that they can come at the uncertainty, the final uncertainty, relative uncertainty is 1.4 10 to minus 18, and limited by the knowledge of atomic response at room temperature. You can do better if you go to cryogenic temperature. This has been done in nowadays in several laboratories. This is a picture of from Kasturi's laboratory, where you can see the frequency shift at room temperature compared to the to the temperature at 300 Kelvin. And the different atoms have different shifts. So it depends, as I said before, where any states that can perturb the transition are in the respective atom. So it can be negative, but it can also be positive for the strontium ion, for instance. You have to measure it and compare it to calculations. You can calculate it, and if you are lucky, comparison and the calculation and the experiments agree, then you have a high confidence that you can apply the correction, but you have to apply this. But if you go further to lower uncertainty, fractional uncertainty is below 10 to minus 17. You also have to consider other transition, E2, M1. It's not only an electric field, but there is also a magnetic field. Usually you say, oh, magnetic field interaction is smaller than electric field. But if you have such an accuracy, and you have to consider this, and okay, and there is a recent measurement by Dersher et al. Published this year that shows you the measurement they have made compared to other measurements and to, this was also a measurement, but also to computations. And if you have a look closely, they differ in the order of 3 times 10 to minus 18. And this has to be considered in the future. Okay. Go to another example of an optical clock, the ytterbium single ion clock. I can go probably a little bit faster now. You interrogate an ion that is kept by electromagnetic fields in a so-called trap. It can be a Paul trap or it can be a linear trap or so. The ytterbium ion has 2 optical transitions. Come on. Okay, I wanted to speed up, but okay, no problem. Yes, I tell you. This is the interrogation light. And there is a transition from this state to this state, and the one other one to this state. Both can be used. This is wrong. E2 should mean is rather insensitive to external field, but due to the very long lifetime of this transition, it means that small perturbations can shift the line more dramatically. And if you want to excite the line, you have to apply high interrogation fields. So the laser has to be cranked up to do this. But this leads to a big shift, and this can be suppressed by the so-called hyper-Ramsey technique that has been developed by Udin et al. In 2010, and it makes use of changing the phase in between. So making a phase shift for the laser, and if you do it right, you can read it, how it is done, then you can suppress this shift dramatically. Yes, here it says the hyper-Ramsey shift So you can use the Rabi oscillation, continuous oscillation, and then determine the shift to first order. Then you apply the hyperency at this frequency, and this is very flat. And that's the reason why you can overcome this largely perturbing shift. Okay. How to determine the black body shift in the ytterbium ion? You have a driving electromagnetic microwave field to store the atoms. This heats up the whole trap to some extent. Even if you would keep it at very low temperature, there is a heating up to these fields. So what has been done by Hundemann et al. Is to measure the influence all over the trap, and then to do the correction. Also, they have applied different lasers to find the exact form of this state in order to make the correction accurate. Okay, the optical frequency comparison has been done between the E3 of ytterbium and the strontium clock, and the instability of the ytterbium versus the cesium fountain goes like this. But if you compare it versus the strontium lattice clock, it goes down by more than an order of magnitude, and you could do comparison in the 10 to minus 17 range within a day or so. Okay, I should also give the uncertainty budget of the ytterbium. In this way, the factors look different. 7 times 10 to minus 70 times 10 to minus 18, the black body radiation. I have shown you how you can reduce it. And in total, they came up with a relative uncertainty of 3 times 10 to minus 8. And they have done measurements over 5 years or so, and this is the result. And it looks, at first glance, it looks not very bad. But if you look more closer, okay, then you would say, this is much lower than here. So I would be very skeptic that there are not hidden effects that have been overlooked so far. Because, yes, but the better measurements are between the E3 and E2 of the ytterbium. So for me, it's clear. I'm a little bit suspicious about this. Okay, that is the status. As I said before, we should not say point about the people and say, okay, one has to look for it. How can we look for it? So we can make comparison between the ytterbium and another guy. For instance, if we could do a 3-cornered head measurement between, say, ytterbium, strontium, and aluminium or anything else, if we could do this, we could see which one is fluctuating. But I have to say that this is not so easy. Each of these experiments are truly long-term measurements, and they need a lot of effort to do this. Maybe something has changed in the, you see, these are more than, I'll say, 600, 700 days, which means 2 years or so. And can you guarantee that nothing has changed in your laboratory over years? You do this evaluation, this uncertainty evaluation, of course, every time you do a measurement. But maybe somebody has overlooked it, or it could be the comparison. I showed this. The two experiments are in different buildings in PDB. You have frequency comms in between, and I will talk about this. Frequency comms are believed to have very high accuracy, but are you sure that in each case, when you do a measurement, everything is all right? So I will show you 2 examples of previously overlooked contributions. The electric field at room temperature is 832 volts per square meter, volt per meter, as I said before, exactly to say the mean electric field. And in 1982, Itano and co-workers have calculated the fractional shift of the black body radiation on a cesium clock to be minus 1.7 times 10 to minus 14. But at that time, the cesium-1 clock of PDB had an estimated fractional uncertainty of 6 times 10 to minus 15. And to be honest, this has not been corrected there. So there was an unseen error at that time. It was not included in the uncertainty budget. PDB measured this in an experimental cesium-1X clock to be 1.66 times 10 to minus 14. So it was clear there is this shift. So then in 1993, already the first cesium fountain clocks were operating with expected fractional uncertainty below 10 to minus 15. And this is a 10 to minus 14 effect. It is 10 times, more than 10 times huger than the estimated uncertainty. So this means there was an action was overdue. Different atomic clocks were operated at different temperature, and so they have to give different frequencies. But these most accurate clocks were used to realize the base unit of the second, the base unit of time and frequency. Oops. Some institute applied the correction, some did not, even worse. So UTC, the coordinated universal time, was not correctly determined within the estimated uncertainties. Okay, how is it done, the universal coordinated time? So there are around 500 different clocks that make a free atomic time to make a stable time scale. This is corrected with primary frequency standards to make it also accurate. And these are by the Timing Institute, and this is then distributed to the users via different means. Okay, that's enough for this to see that an error here directly contributes to UDC. In its 13th meeting in March 1996, the Comité Consultatif for the definition of the second, then acted. I have shown last night that the meter convention has several helpers, say, consultative committees on the different systems. And one of those, the consultative for time and frequency, considered this and said we have to act. They made a recommendation stating that a frequency shift correction compensating for the PBR frequency shift shall be applied to the reading of the primary clock. As I said before, not all have applied this correction. Measures were taken to adjust, and then we have the problem that the scale of UTC is off. We make we apply a correction, then the scale of the second would change. It's also not so nice. So what they have done, they steered it gently from the old value to the new value. And yes, and this was told how to do this. It's a little complicated process, but it worked. And after this overlooked contribution, the world is okay now. Okay, let's have a look to something I have personally overlooked in the past. We operated a calcium atomic clock. That was a beam clock. Calcium beam went like this. And we excited the beam with an optical laser beam in this direction. So we had 4 interaction zones that gave optical resonances with where you can easily find the center of the transition. And we made an uncertainty budget. But if you look at this, you don't see the effect of a Sagnac effect. We didn't know at that time. But then in 1989, Christian Bordet showed that the interaction geometry comprising 4 traveling laser waves, which is used to obtain optical Ramsey fringes in atomic spectroscopy, is also well suited to build an atomic interferometry based on the atomic recoil. So what this means is the atomic wave, the wave packet, the atom, if it enters the first interaction zone, interacts with the laser beam. And as I showed before, the interaction leads to a recoil. And what you really do in this experiment, you adjust the power in this beam to such a way that you have equal probability of 50% that the atom is in the ground state and 50% that it is in the excited state. So we have a beam splitter for atomic waves. And the next one does the same thing. There would be a beam splitter here and a beam splitter here. I did not write all the things, but in effect, you have an interferometer. And you look for the Ramsey resonances at the output. Okay, but if you now rotate the whole system, then it happens, if you rotate it clockwise, it means that this partial wave first come here and this partial wave will be delayed here. Now this clearly gives a shift of the interference pattern. This shift is well known in optical cases. There it's called the Sagnac shift. And we have used an experiment where we put our apparatus onto a rotary stage. This is the atomic beam. Here is the oven. It goes in this direction. Here is the detector. And here are the 4 exciting laser beams. Okay, and what we saw is in fact that the shift would be as large as 5 kilohertz or so, depending on the rotational frequency. Okay, but if we now think that our experiment was on the rotating Earth, we have to expect such a shift. And if you calculate it, the effect for our atom interferometer results between 0 hertz at the North Pole or South Pole and 11 hertz depending at the equator, depending on the latitude on Earth. So in principle, we had to use a Sagnac effect corrected for the position or the latitude of Braunschweig, which is on the order of was below 5 hertz. We had to subtract it, but we didn't do it because we didn't know that we operate an atom interferometer. And so there was an error that was not recognized at this time. Okay, now I would like to talk about methods to reduce the uncertainties and the errors. So we have several times talked about an uncertainty budget. And it's a bad habit to do first a measurement and then establish an uncertainty budget. Because what is the reaction? What would be the reaction of me? If they agree, the measurement agree with the previous measurement, I would say, I'm happy. And it's not so important looking for the uncertainty budget in much detail. But this we call sometimes intellectual face locking. We lock our behavior to a result that is not correct. So you have to establish an uncertainty budget before you do an experiment. Other case, if you look to the experiment and see this does not coincide, it's off by plus 5 hertz with respect to another standard, then you first of all look for effects that shift in the positive direction. And you do not care so much about the shifts in the negative direction, but because these could also increase the shift even more. So it's good habit to do the uncertainty budget before you do an experiment. Then the next thing we have learned yesterday, of course, check measurements by repeating them. So it's the repeatability that matters. Einmal ist kein Mal, we say in German. One time is not measured. If you measure once, it's not measured at all. So you have to do several measurements. I have shown you the comparison between the strontium and the ytterbium clock. If I had only done one measurement, I would have been happy and said, oh, it's within the uncertainty budget. Everything is all right. But doing this measurement over a longer time, we are now able to have some doubts that the uncertainty has been calculated correctly. So the other thing that is important, change the use parameters of the experiment. And is the result still the same? Yeah? Do the measurement during the nighttime and during daytime. You can find problems at this step because during the nighttime, usually the lab is empty. During daytime, a lot of noise going on. It can shift the frequency. And so you can use This method to change the parameters of the experiment to find hidden errors. Other thing is, for instance, I do not stay all the time with PDB. In CIRTE, the National Metrology Institute in France, in Paris, there they have this underground tube that goes very close to the laboratory. And if the train is accelerating, there are huge currents flowing there and also huge magnetic fields. And they do the measurement when they observe this only between 1 o'clock in the night and 4 o'clock in the morning when there are no trains run. It's not in with clocks with single iron clocks in Vienna. No, not Vienna, in Austria, I say. They have observed that the elevator can produce large currents. Yes? Things like this you can identify if you do measurements at different times with different conditions. It's also very nice if you crank up the power of your laser doing the interrogation, and you have, of course, to do the correction for the correction for the intensity in your uncertainty budget. And if they do not agree after the correction, you should think about this. So, okay, enough of the examples. The best method of all is to check, to use different methods. That is simple. You have to take different power meter. Power meter is a typical source of error. You have a power meter in the laboratory, you do the measurement, and if, for instance, to calibrate the AC stark shift or so, you have to know what is the intensity of the beam. But do yourself the pleasure taking all the power meters in your laboratory and compare them with the same laser. Sometimes you get crazy about this. Calibrate the power meters. It's a service you can get from a National Metrology Institute, but you can also get it from a company. So if you have a calibrated power meter, then use secondary standards, and in every 2 years or so, redo the measurements. That is sort of a quality management system you have in the laboratory. That is also even more critical with temperature sensors. You have seen for the clocks, temperature sensors were used to measure all around the strontium clock. And I have talked to Juni about this, and he has said he has sent all the sensors to the National Institute of Standards and Technology in Washington or Gaithersburg to calibrate them. And they were not really fond about this, but I did it for the colleagues who used 18 or something like this, different sensors. Yes, you at least have, if you do measurements, you have to calibrate them. Okay, I show you a more complicated example from our own laboratory, the measurement of optical calcium frequency. So what you do is you have nonlinear response of the detector. For instance, if you have such a thing, then the detected power is a function of the voltage is nonlinear. And if you would use a diode, for instance, it's really nonlinear here. So the power you measure depends on different powers of the voltage, U squared, U3, and so on. So you have different frequencies. This is a simple model for frequency doubling or triplication or quadruple and so on. Okay, we have used this in our first measurement of the calcium standard I have talked about some time ago, where we have directly connected the cesium frequency standard via a hydrogen maser to the optical calcium frequency standard. This chain, which we called it, we had a diode laser at half the frequency. We frequency doubled it, stabilized it, so that we were sure that it is exactly 1/2 of this frequency. And we did this all the way down till quartz oscillator at 22.7 gigahertz. And here below in the chain, I called it always the DC part of the chain, we had high multiplication factors there. But we put all together in the night and measured the frequency of calcium several times. Okay, that was calcium. Calcium standard, the one I showed before, the calcium 40. 40. It is the experiment. Go back here, where the calcium atomic beam was used. No hyperfine. That is the nice thing with calcium 40 is doubly matched. 20. Yes. Okay. So no hyperfine splitting also. Okay. Good. We did this measurement and we're happy with it. Gave it an uncertainty, 430 hertz or so. And the contribution of the chain where we were suspecting, do we have glitches? Do we lose a cycle anywhere or so? We calculated this and we're happy. And then the frequency measurement using a femtosecond was possible. I always said to Ted Hensch, you have seen our funny chain and thought about that must be easier. So in a way, we were responsible for the for the frequency chain. That's a joke. Okay. You know, you are familiar with this. So we built in PDB a frequency measurement of the calcium frequency with a laser. A frequency com, it was different at that time. It was a high sapphire laser with a cesium saturated absorber in between to make all these things. Apart from this, it was nowadays the typical experiment. And before we did this experiment, I had this feeling in my stomach. Will there be the same value as we have determined 5 years ago I talked to Harald Schnatz, who was the main author of the frequency measurement chain. And he said, I sleep well. Don't you remember how carefully we did the evaluation? Okay, I said, yes, I tried to remember. And my stomach, the problem in my stomach gradually became smaller. But when we got the result, yes, they agreed. So I will not recommend you do all the big things again in order to make different experiment, but sometimes it's useful. Here it's simply because a new technology showed up. Okay. Measurement of frequency is usually believed to be accurate because what you do is you simply count. You count different frequency in a beat note, for instance. One laser gives you this frequency, the other one this. And then if you add these frequencies, you get something what looks like this. The detector will not follow the high frequency variation, but it will see such a signal. This you can measure by comparing the two standards and using a frequency counter. So where is there space for errors? There are many rooms for errors there. Some of them, I will not say I have made all of them, but some of them. So what you have to do, first of all, is to use a filter. Otherwise, you get spurious other frequencies and things like this. Even though Professor Charlotte said to Professor Hensch, never measure anything other than frequencies. This is probably correct, but do the frequency measurement very correct. So spurious signal with other frequencies can perturb. The best thing is use a spectrum analyzer and look what's going around. Then use filters, change the filter bandwidth, look if the frequency that is measured is changing. If so, you have a problem. Okay. This is also an often made error. You have a frequency counter that has an internal frequency generator, a quartz oscillator, for instance, that gives the reference frequency. If you make very accurate measurements, the uncertainty of the built-in oscillator is typically between around 10 to minus 7 or so. The fractional uncertainty. So if you take, let's say, a signal of 100 megahertz, and 10, which is 10 to the 8 hertz, and your inaccuracy is 10 to minus 7, you make an error of 1 hertz. Yeah? So the receipt to change, to solve this problem is easy. Each one of these counters has an input for a reference frequency. You could put in there Josephson standard, as I have shown yesterday in the evening, or a rubidium clock, or you could also use the frequency transmitted by PDB's long wave transmitter, or anything else you are aware of that can be used to stabilize your oscillator that gives you a well-defined frequency. And I have talked to some of my colleagues, and one came and said, yes, the first measurement of the ytterbium ground state frequency, we have made this error. We have locked the frequency to a GPS discipline oscillator, but we forgot to put up the antenna so that the GPS signal could be received. And you will not get it inside your room. The laboratory is usually very well shielded, so you need an external antenna. So these are a few examples to be cautious about frequency measurements also. Another thing, your signal is usually noisy. So if there are additional, if the noise is like this, the counter will count this as a zero count, going through. So the noisy signal can produce additional zero crossings, or it can also give, if the noise is too loud, cycle slips. And we learned with this frequency chain, I could see it in the night. If the signal to noise at a certain stage went down below 30 dB, also cycle slips occur. So you have to do very good signal to have very good signal to noise. Okay, go on with this. We have talked about this. So compare with an experiment of others, if it is possible. Yes, you can use calculated frequency, you can use published frequency. You could build a second one of your clock of the same type. If you don't do it the very first instance, but later. But you could also compare it with external clocks that are far away. There's a possibility to do worldwide clock comparison, either via two-way satellite time and frequency transfer to geostationary satellite, common view with GPS or GLONASS, Beidou, Galileo versus medium Earth orbit satellite or low Earth orbit satellite with optical transfer. This is not possible regularly. You can transport your clock to a different place, or you could use fiber links. I have shown you between the frequency, during the frequency comparison between ytterbium and strontium. We have used such a fiber. Fibers have been used with COM, where you use your laser to COM, put a transfer laser through the fiber, use a COM there and compare it at the next institute. Nowadays, we have fiber links in Europe, very many. We could compare PDB's laser with Sirte's laser and NPL's laser. We have a transportable laser that has been transported to the Alps to do some geodesy and metrology. We can do clock comparisons via satellite, two-way satellite time and frequency compare. And even if these things are microwave links, you can use a frequency COM, link it to your fountain clock or your clock realization you have. You transfer it this way and do the same thing at the other way. This is often done. Okay, there's another interesting thing. If you have, for instance, a frequency ratio between clock A and clock B and clock C. Frequency is a ratio between A and B, B and C, A and C, then the product should be unity. So if you have a laser or a frequency standard, you could use things like this. This means you can transport this information via an email. That is much more convenient, of course. Okay, how can we get confidence then in a new definition of the second? I have talked a lot about the optical standards now, and we have talked about yesterday this curve of the cesium clocks, but in the meantime, optical clocks have achieved much lower uncertainties, but not the accuracy, because the accuracy depends on the definition of the time and frequency, and this is the cesium clock. So we have only estimated uncertainties to find the true line center of the transition. And okay, if we want to use this, we have to make a new definition. And how can we get confidence? So we use every now and then we use all the measurements and make and get a list of frequency that is then approved by the CCTF last time 2022, and then you come up with frequencies for so-called secondary representations of the second, with uncertainties in the order of 10 to minus 16 or so. So what you can do if you do a measurement compared to this. Okay, and we have talked about what else we have to do to come we should show at least that 3 clocks come down to 10 to minus 18 or so. We should have comparison. We should have regular contribution to the atomic time and so on. And if everything is working, then we believe that we can do a new definition of the meter, but maybe there will be surprises. So, yes. No, roughly 50%. And since I made this slide for the CCTF, you also see that I was extremely optimistic that the definition is, but that was agreed that these are the preconditions to make a new definition of the meter. Regular contributions to TAI, there are less than a handful. No, and not really regular, there are 2 or 3. So this is not, two comparisons between 5 clocks with uncertainty smaller than 5 times 10 to minus 18, not at all, not yet. I have shown you a comparison that was rather 10 to minus 17 or so. Okay, things like this, we are still a little bit away from that. Okay, okay, further method to reduce the uncertainty. It is usually as important to minimize uncertainties as it is to quantify them. There are some good practices which can help to reduce uncertainties. As I have stressed the point, you should use a quality management system, recalibration of the measurement devices, check the reference value, check the traceability of these results, whether it is really connected to GPS also. You can use traceable references that could be you could get from the calibration hierarchy, either National Metrology Institute, okay, Bureau of Indian Standards or so, but still use the one you really need. That no makes sense to go to the BIS and ask for a calibration of a voltmeter with 10⁻⁸ relative uncertainty. Okay, so help others to do good measurements, what to do with a broken measuring device, put it into the cupboard and close the cupboard, not the best way. Discuss with others the mistakes you made to help them. As I told you, some of the mistakes I made. Avoid simple pitfalls, like if you use the scale of the meter, usually the uncertainty is referenced to the full scale. So don't use it at 10% of the scale. Uncertainty will be higher. Then avoid calculator and software errors. When we calculated the frequencies of these optical standards in the order of 10 to 16 or so, 10 to -16, usually double precision is no longer accurate. You have to think about this, but it's an easy way out. If you look for the mean value, you need only the last few digits. You can calculate this. So things like this. So I have a minute for famous experiments. Electric charge, you know, Millikan experiment, oil drops falling down, applying electric field to counteract the gravitational acceleration, and with the electric acceleration, and I can leave this, you can look it up in Wikipedia, for instance, how it's calculated, and Millikan found that there are distinct levels for the electric charge. But he published this result, and there was some, and now we know how accurate he was. He claimed 1 sigma, and it's now 3 sigma off. It's not dramatically bad, but beware that people could check your measurements later. So I can leave this out, but be honest and give all the details of your experiment. For instance, there was a reanalysis of the Erdős experiments to find a possible 5th force after 60 years. They looked into the notebooks, the early ones, and checked this. So care for your notebook. Make sure that you put all the things there, either in electronic or on paper. And then the last example, measurement of the gravitational constant. The status right now, this is the mean value. But if you would count that with 1 sigma, there should be each 3rd experiment being an outlier. But if you count this, that are within the uncertainty is 6 to 12, the wrong way. So still a problem right now. We don't know what it is. There's a system, there are systematic differences. One has been found in the experiment of PDB that was even further away. And if you make an error, which can happen, and you know about this, you have to write an erratum and show that nobody else falls into the pitfalls. Okay, that was what I wanted to tell you this time. Thank you very much.
Questions?
Sir, in slide number 13, you
13 or
13, sir. Sir, 13, sir. The next one.
Yes.
That graph for the strontium.
I come up to
Graph, some graph.
Sir, 11, sorry, sir. Yes, sir. So
this one.
this one, sir. So, sir, generally we would expect that the first order Doppler shift is much more higher than the second order. But here, just by shifting one energy level, we are seeing that it's following the second order Doppler shift. So why this one is coming, sir?
So in the first order Doppler shift is dramatic if you have free flying atoms, for instance. Then you can get megahertz to gigahertz or so. But here now you are in a well there. So you are not allowed to have all the velocities, but only the velocities are quantized here that are allowed to be motional velocities is 1/2 plus h bar, the oscillation frequency in this well plus. So it is fixed in a way. And this means if it is concentrated to less than a wavelength of the optical wavelength, there is no longer possibility of the first order Doppler shift. But there is a possibility to the time dilation shift. For instance, this was a problem, I should have addressed this. When you start with a hydrogen maser or the hydrogen maser, the wavelength is 22 centimeters or so. You can afford for containing it within 20 centimeters, so you are also Doppler free. But with the wavelengths going down below a micrometer, you have problems also. But if you confine to smaller areas, then the first order Doppler shift is gone. Does it answer your question?
Yes, sir.
Yeah, so I have a few questions. The first question is, in the beginning, you mentioned about molecules can be also used for atomic clocks. Molecules.
Molecules,
Yeah.
yeah.
So even like there are like other like proposals recently that highly charged ions or nuclear clocks can be made. So according to you, which candidates can be like thought of as a most potential?
You asked me for the prospects of molecular clocks.
Whether it's molecules or highly charged ions or nuclear clocks.
Yeah. So nuclear clock, if we find the transition, eventually, that was a nuclear clock is you have transitions also in the nucleus, thorium, for instance. And when we got across this idea in 2000, when I became head of the division optics, we decided to make a group that cares for this for 3 years. But we haven't found yet this transition really to do this. So it's now the 6th prolongation of the project or so. So we have to find the transition, then we can do it. And this has a very nice system because the electron shell is shielding the nucleus. So the nucleus has much less perturbation, but still there are perturbations. So we have to see it. They're highly charged ions, where you throw away all the outer electrons, but the internal one or 2 or 3 are really a nice system, and we have to look up. But they are also, they have perturbations. Some of them you calculate, for instance. I think we have to watch the competition. Which one is the best one? And then we work on this. But unfortunately, when I was head of the division, I was asked very often, what will be the best clock? Neutral atoms or single or ions? And I said, look at PDB. PDB operates both because we cannot decide at that time which one is the best one. If we cut off one, it might be the case that this will be the future clock and vice versa. So, okay.
Oh, my second question is now, you highlighted one point that when you repeat these measurements, clock frequency measurements, at different time you see, different, frequency values or something like that. But many people are trying to prove many fundamental physics, like various fine structure constants or dark matter and like that. So then do you think that using this kind of measurements, we can still prove that?
Yes, but there is one point when you look for the proposal of Thiruvananthapuram, that is, and that there is dark matter coming across the Earth and give such a result. You cannot repeat this measurement. That is a bad thing with this. A single result you cannot repeat. It could be the case, but if we go further and do more measurements, we might see such effects, but we cannot rule it out. It could, but the fine structure variation we can rule out, because the measurement in the ytterbium ion, there are 2 different transitions, and the ratio of both transition contains the fine structure constant. So they have measured this over years and did not find a change in the ratio. So at least at this time, it is lower than 10 to minus 17 per year. So, and this, what we saw was rather 10 to minus 16 per year. 10 to minus 16.
Okay, my last question, that these days also many people predict that there could be some kind of new vector bosons present within the atomic systems, right? That through isotope shift measurements, people are trying to prove that. So if such particles exist, and then there will be new interactions, and that can also cause a frequency shift and like that. So that may also go into your...
No. You cannot include quantitatively things that have not observed.
No, this is a possibility, like if you see some kind of fluctuations, maybe from that fluctuations.
Maybe, yes. And there is a new paper from Hundemann's group this year, 2013. The first author is Melanie Pilsinger or so. This, a few weeks ago, they have given bounds for such extra particles. I can give you the reference.
Okay, yeah. No, no. Acha. Yeah, yeah, okay. Do you have a mic?
Sir, for on the number 13 slide, we,
And
so
number?
13.
13.
This one.
Next.
Sir, on that table, if we see that BBR shift is coming negative, and for the PTB measured, there is BBR shift is coming like.
You are perfectly correct. When I went through the transparencies last night, I said, should I write this again? Then I said, I will go to my colleagues and urge them to do next time include the sign of the correction. But it's not wrong because it said corrections. The correction is right, but it left out the in which direction the correction is. And it is much better to do it like this. You are perfectly all right. I didn't do it last night because I would have to look up all the papers and go through it. Yes, good.
Anders?
And I'm not responsible for this, no.
Yeah, can you tell how the mercury optical lattice clock compares to ytterbium and strontium?
Mercury lattice clock. Yes, they are okay. I have given rather briefly the list of recommendations for the secondary standards to be used for time and frequency. I will not click through it. I think it's 2 × 10⁻16. And the mercury clock is a valid competitor, I would say. But it is, yeah, it's also people work on several places. I'm not sure if Kasturi has also made a transportable clock like this. Yes, the good thing with it is it's very heavy. Black body. A black body. I don't remember. You know it because it's better. It's smaller, yes. But okay, we have to see what will be the outcome.
Okay, if there are no further questions, then let's thank Professor Fritz Riehle for his 3 very nice, exciting talks. And on behalf of the organizing committee, I'd like to give a small memento to him.
Thank you very much.
Thank you.
Beautiful. Thank you.